Welcome to our presentation on time series regression, where we will delve into ARMA and ARIMA modeling using EViews. This session will cover the core concepts of analysis, estimation, and diagnostics for these powerful time series models. As the quote suggests, these models are fundamentally about understanding and modeling the persistence or memory within a variable over time. Imagine trying to forecast tomorrow's stock price. You wouldn't just look at today's price, you'd consider the trend over the last week or month. That's the essence of modeling persistence. So why can't we just use our standard regression techniques? Let's explore the unique nature of time series data. When we work with cross-sectional data, each observation is typically independent, meaning one data point doesn't directly influence another. For instance, my height doesn't predict my neighbor's height. This independence is a fundamental assumption for many standard statistical methods, including ordinary least squares, or OLS. However, time series data is fundamentally different. It possesses a memory, where today's value is heavily influenced by yesterday's, and even past errors. This characteristic is known as persistence or autocorrelation. The graph on the right illustrates this dependency. The Box-Jenkins methodology provides a systematic, four-step approach for building robust time series models. It begins with identification, where we assess the data for stationarity using tests like unit root tests, and examine the autocorrelation and partial autocorrelation functions to understand the underlying patterns. This is crucial because stationarity is the prerequisite for reliable ARMA estimation. Next is estimation, where, based on our identification, we select the appropriate orders for our autoregressive, moving average, or integrated autoregressive moving average model, and then estimate its parameters. Following this, we perform diagnostic checking. The core question here is whether the model's residuals are white noise. Achieving white noise residuals is the ultimate proof of our model's success, meaning we've captured all the predictable information. Finally, with a validated model, we move to forecasting, which can be performed dynamically or statically. Throughout this process, parsimony is our goal, finding the simplest model that adequately fits the data. The first question is always, is the series stationary? If the answer is no, we must apply differencing, typically denoted as d equals 1, which leads us to an ARIMA model. The I in ARIMA stands for integrated and signifies this differencing step, representing the number of differences required to stabilize the mean of the series. If the series is stationary, we then proceed to examine its autocorrelation function, or ACF, and partial autocorrelation function, PACF, plots. When the ACF decays gradually, but the PACF cuts off abruptly after a few lags, it suggests an autoregressive, or AR model. An ARP model implies that the current value of the series primarily depends on its own past values, reflecting its historical patterns. Conversely, if the PACF decays slowly and the ACF cuts off sharply, it points to a moving average, or MA model. An MAQ model indicates that the current value is influenced more by past shocks or innovations. Finally, if both the ACF and PACF decay slowly without a clear cutoff, it might suggest a process with long memory, leading us to consider an ARIMA model. This systematic flowchart helps us precisely identify the underlying structure and select the most appropriate model specification. We've talked about these AR and MA components. Let's now look at the actual equation that brings them all together. This equation is the engine of an ARMA model, representing the value of our series at time t, denoted by RT. The first part is the autoregressive, or AR, term. It captures how RT is a weighted sum of its own past values, RT minus I. The phi coefficients quantify the persistence from the series' own history. Next, the moving average, or MA, term models RT as a function of past forecast errors, AT minus I. Here, the theta coefficients measure the persistence of these random shocks or innovations. Crucially, AT is the current shock, and it must be white noise, completely random and unpredictable, for the model to be valid. For example, if we model daily sales, the AR part accounts for how today's sales are influenced by yesterday's, while the MA part explains the lingering effect of unexpected sales surges from previous days. This equation provides a powerful framework, but it relies on critical assumptions that we must always verify. To build a reliable ARMA or ARIMA model, 3 critical assumptions must be met. Firstly, stationarity is essential. This means the series mean and variance must be constant over time. For the autoregressive, or AR components, this translates to the characteristic roots, or phi values, having an absolute value less than 1, ensuring they lie within the unit circle. Ignoring this risks spurious regression. Secondly, invertibility is crucial for the moving average part, allowing it to be expressed as an infinite AR process. This requires the absolute value of the MA roots, or theta values, to also be less than 1. Finally, the model's residuals must be white noise. This confirms our model has captured all systematic patterns, leaving only unpredictable random errors. Remember, if a process's roots lie on or outside the unit circle, it is non-stationary, and we must apply differencing to force stationary, which is the I in ARIMA modeling. Adhering to these conditions ensures a robust and interpretable time series model. To begin estimating your time series models in EViews, there are a couple of primary routes. The fastest way for a quick analysis is using the command line. You initiate the estimation with LS for least squares, followed by your dependent variable, C for the constant term, and then specify any autoregressive or moving average components. For instance, LSYC AR1 MA1 would estimate an ARMA 11 model for variable y. For more robust and permanent model storage, it's recommended to create an equation object. This can be done by navigating through Object, New Object, Equation in the EViews menu. It's important to remember that ARP and MAQ are reserved keywords in EViews, simplifying the model specification. Once you've entered your command or opened the equation window, you'll then proceed to configure the specific details of your estimation. Once you've decided on your model specification, the next step in EViews is to configure the estimation settings. In the equation specification box, you define your model. Here, we're modeling d of log vol, which signifies the first difference of the log of the volume variable. We include a constant c, which should always be present unless specific theory dictates its exclusion, and our autoregressive AR1 and moving average MA1 terms. For the estimation settings, the method is typically LS least squares, and it's important to remember that EViews automatically handles the complex nonlinear iteration required for ARMA models. Finally, the sample field allows you to specify the exact time period for your estimation, which can be dynamically adjusted to analyze different subsets of your data. This window is where you tell EViews precisely how to build and run your time series model. For our case study, we're examining NYSE volume data. The crucial first step in any time series analysis is data preparation and inspection, starting with a visual check. Observing the raw plot, we clearly see an upward trend, indicating a non-constant mean over time. Furthermore, the spread of the data points widens as the volume increases, forming a funnel shape. This signifies non-constant variance. Both of these characteristics are classic indicators of a non-stationary series, which violates a core assumption for ARMA and ARIMA models. To achieve stationarity, we apply specific transformations. Taking the logarithm helps to stabilize the variance, effectively removing that funnel shape. Then applying differencing stabilizes the mean by removing the trend. Our goal is to work with the transformed series, represented as d log of volume, ensuring it meets the stationarity requirement for effective modeling. After running our ARMA model, we analyze the output. First, we examine the prob column. P-values less than 0.05, as seen here for the constant, AR1 and MA1 terms, confirm that these coefficients are statistically significant. Next, regarding model fit, remember that for differenced time series data, R-squared can be deceptively low. It's more appropriate to compare models using information criteria like AIC or SIC. Finally, a crucial check is the inverted ARMA roots found at the bottom of the output. For our model to be stable and interpretable, these values must have an absolute value less than 1. In this case, 0.40 and 0.75 are well within the unit circle, confirming our model meets the necessary stationarity and invertibility conditions. After estimating our ARMA model, Step 3 is dedicated to stability diagnostics, a critical check for ensuring our model is well behaved. EViews provides a clear visual for this, the unit circle plot. This graph displays the inverse roots of the autoregressive and moving average polynomials. For a model to be stationary and invertible, all these roots must lie strictly inside the unit circle. This is a fundamental requirement for reliable time series modeling. If a root were to fall near the edge of the circle, particularly close to 1.0, it would signal that our series might still require additional differencing to achieve full stationarity. Looking at our results, the AR roots are at 0.81 and negative 0.10, and both are clearly positioned well within the unit circle. This confirms that our ARMA model satisfies the necessary stability conditions, allowing us to proceed with confidence. This is our final and arguably most critical diagnostic step, examining the correlelogram of the residuals. A well-specified model should leave no significant patterns or information in its errors, meaning the residuals should be white noise. This is our final and arguably most critical diagnostic step, examining the correlelogram of the residuals. A well-specified model should leave no significant patterns or information in its errors, meaning the residuals should be white noise. Visually, this means both the autocorrelation and partial autocorrelation functions should appear flat, with their bars staying well within the dashed confidence bands. More formally, we rely on the Q-statistic probabilities, where the null hypothesis is that the residuals are white noise. We are looking for high p-values, specifically greater than 0.05. As you can see from the table, all Q-statistic probabilities for various lags are comfortably above this threshold. This confirms that we cannot reject the null hypothesis, allowing us to confidently conclude that our residuals are indeed white noise. Our model has successfully captured all the underlying dynamics of the data, leaving only unpredictable noise. Now that we have a well-specified, stable, and validated model, we can move on to the final step, forecasting. Now that we have a well-specified, stable, and validated model, we move to the final and most anticipated step, forecasting. EViews makes this straightforward through the Forecast dialog box, as shown here. You'll specify the forecast equation, the series to forecast, and the forecast name, which in our example is log vol ARIMA. Crucially, you'll define the forecast sample over which you want to generate predictions. The slide highlights two critical forecasting methods, static and dynamic. A static forecast is primarily for one-step-ahead validation within your existing sample, using actual past values for each step. In contrast, the dynamic forecast, which is selected in our example, is essential for true out-of-sample, multi-step predictions. This method generates a forecast path by using its own previously forecasted values for subsequent steps, not requiring actual future data. The resulting graph shows the actual values, our dynamic forecast, and the associated confidence bands, giving us a clear picture of the projected future behavior of the series. This powerful quote encapsulates the fundamental purpose of time series analysis. It's about more than just numbers. It's about uncovering the narrative woven into the sequence of data points over time. We're essentially trying to understand how a variable's past behavior, its memory, or persistence, influences its present and future. This understanding is crucial because, unlike cross-sectional data, observations in a time series are inherently dependent on each other. By listening to the story the data tells about its own past, we can build robust models to explain phenomena, identify underlying patterns, and ultimately make more accurate forecasts. For those interested in delving deeper into the theoretical foundations and practical applications, we've drawn upon primary resources such as Box, Jenkins,